Welcome, everybody. My name is Gabriel Gleizer. I'm a PhD student under the supervision of Manuel Mazo Jr. at TU Delft. Today's presentation is about scalable traffic models for scheduling of linear periodic event-triggered controllers.
Event-triggered control is a sample and hold controller where instead of sending the data periodically, you do so through a condition checking mechanism that depends on the state. The idea is that you only send the data when needed, and by doing so, you can reduce the communications, which is especially important when you have multiple loops sharing a network. However, in an actual network, it is very hard to schedule multiple loops that are using ETC. This is very easy to see, for example, when you check multiple loops using periodic sampling and they all share the same period, it's easy to create a fixed schedule or use something like round robin to schedule successfully the communications. However, in ETC, because the timings are less structured as they depend on states, something needs to be done real time with respect to scheduling to avoid conflicts. To do scheduling for ETC, we need a model. Even though the traffic is erratic, it's too predictable. However, even for linear systems, predicting inter-event times is not easy because the time model itself is nonlinear. Also, it's important to notice that scheduling involves discrete choices like ordering, and this is among the reasons that we choose to do discrete state traffic models, which are called abstractions. Now let's take a look at periodic event-triggered control, which is a special case of ETC that we focus on in our work. We're also focusing on linear systems with a static state feedback and types of conditions that are called quadratic triggering conditions. So the triggering here will only happen when this quadratic function, depending on the actual value of the state and the last sent state, which is psi hat, is positive. Well, periodic event triggered control is equipped with a timer, and this condition is checked only periodically. Then you choose a check-in time, h, and your inter-event times will belong to the set h, 2h, 3h, so on and so forth. If you impose a maximum inter-event time, you then can only get a finite collection of inter-event outputs. This maximum inter-event time is very common because generally we want a heartbeat of the system. With that, we can construct a PETC infinite state traffic model. This is easy to see because first, notice that the current state value is a function of the inter-event time and previously sampled state. So whenever you sample, you can know exactly what will be the state through this equation using simple linear systems equations. And this can be condensed with a matrix M of k, where k is your inter-event time, multiplied by the previous state value x. Now the inter-event time is also a function of the sampled state. You just have to check among our finite collection of k's whether this triggering condition is positive, and in the worst case when k is equal to k bar. Notice that we can condense this triggering condition by putting all of the terms dependent on k on this matrix N of k. And so you have a function that is quadratic on x, the previous state, and depends on this finite collection of n matrices. Now this gives the following infinite state model. X plus our next sampled state will depend on m of kappa of x times x. And our output that we're interested for scheduling is this inter-event time. Now there is previous work on finite state traffic models for scheduling. This is work by Colariani, Adzikia, and Mazo Jr. And they did this through what they call the power quotient system. Let me explain a bit what it is. The power quotient system is a system where you divide the state space and each subset of the state space of this partition is associated with an interval where your output, the real system's output, is sure to belong to. They achieve this in event-triggered control by what they call isotropic partitioning of the state space. So they notice that states along a line through the origin share the same inter-event time and the same evolution. Therefore, states with similar direction will have similar behavior. And then you can chop the state space with n minus 1 directions, creating pyramids that stem from the origin to infinity. And with this, you can cover the whole state space. After you have this partition, you compute the inter-event time interval a posteriori. Well, the advantages of this is that you can work on Rn, you don't have to work on compacts. Your partition is composed of convex sets, and the transition maps are computed through convex problems. However, you have still the curse of dimensionality, because in Rn, you have to chop exponentially on n minus 1 dimensions. And also, refining the partitions do not guarantee the shortening of intervals, which is true, for example, if you have a discontinuous map of outputs, which is the case for PETC. Our approach then is that instead of partitioning state space and computing times, we partition time and then determine the states. This is a quotient model. This becomes very easy to do actually in PETC. Then you obtain an exact simulation in contrast with approximate simulations that are obtained in previous work, and the number of abstraction states is independent of the state space dimension. So how is our quotient model? Well, this concept is available in the book from Taboada, Verification and Control of Hybrid Systems, a Symbolic Approach. And in our case, it's a bit easy to see. The quotient state set is the set of all states that share the same output. So if two states have the same output, they become related. So we can collect for every given inter-event time k all the sets that have this inter-event time. And it's easy to unfold this set qk because the set description becomes a conjunction of quadratic inequalities, where all predecessor times of k have to be non-positive, and finally it becomes positive at k. In state space, this is represented that for each inter-event time, you have a collection of double cones, of quadratic cones. Now the problem here becomes when you have to compute the transition maps, which are necessary to have a transition system. We have to deal with the non-convexity that is associated with the states. So far, our quotient state set, in this example, gives us these four discrete states, 3, 4, 5, and 6. Now, a transition from Qi to Qj exists only if there is an X in Rn such that it belongs to Qi, and these are the sets of inequalities that are associated with it, and its successor, Mi of x, belongs to Nj. These are the sets of equations that are associated with it. So one example, we can check that there is this state that starts at k equal 4 and lands at k equal 4. If such a state exists, then we throw an arrow from 4 to 4. Now we check another state from 4 that actually lands in 3. And then in our abstraction, it goes from 4 to 3, another transition. Now this problem, even though it's non-convex, can be relaxed to a convex problem through semi-definite relaxations, where you lift the variable x to a matrix that is semi-positive definite, and then every inequality like this becomes an inequality of trace of x times q. The cost of relaxing is that you get spurious transitions in the abstraction. For example, we can have an arrow from 4 to 5, even though there is no state in the real system that starts at 4 and goes to 5. Now for scheduling, notice that our system so far is autonomous, and the scheduler needs to intervene sometimes. Therefore, we propose to augment the model with early triggering that is commanded by the scheduler. So our model so far has only arrows that are associated with the exact triggering that the plant would have. So we can also compute transitions for earlier inter-event times and check the transition maps. They can also be solved with STP, similarly to what we presented before. Now, from the perspective of the scheduler, the natural triggers, the black ones, are uncontrollable. However, the early triggers are controllable. They are dictated by the scheduler. With that, we can compose the scheduling problem in a similar way as our predecessors did. The network can be represented by a timed automaton, which starts in idle state. And whenever it receives a communication, it resets its clock and it starts running and it goes to the state in use. Whenever the clock reaches the channel occupancy time, it gets done and goes back to idle. However, if another communication is fired before, there's a conflict, and then we go to this bad state. And this is exactly the state that we want to avoid. Now, we can transform our models to timed automata as well because they are semantically equivalent. So the time, the inter-event time, is associated with the clock for each plant. And whenever the clock reaches the inter-event time of the discrete state, you have to leave the state. However, in these other discrete times that are early, you can fire this early triggering and transition before. Every triggering, whether early or natural, fires this communication symbol that is received by the network. So this is a synchronizing action that makes sure that we can compose this network of timed game automata. And this timed game automaton can be solved using the software called Upal-Tiga. Here's a fragment of what would be a strategy for this game. If a system 1 is in Q6 and system 2 is in Q4, then you check the time. Whenever C1, the clock, is equal to 5 and C2 belongs to 1, 2, 3, then you have to do early on system 1. And then you have a similar condition for system 2. So it's a map from the discrete states and the clock valuations to an action, in our case, the early action. This becomes a closed loop scheduler that checks the information real time and decides when to trigger early or to let the systems trigger. Now let's take a look at numerical results. We have a case study with two four-state plants sharing a network. This plot represents the transition relations between the discrete states to the successor discrete states. Whenever there is an X here, there is a natural trigger from one region to the other, and the circles represent the early actions, where K, the inter-event time, is equal to 1. Here we can see the simulation of the networked control system with the scheduler. The top plot just shows that everything is nicely converging, it's the usual thing. The interesting plot here is on the bottom. This is some sort of Gantt chart where the X's again represent the event triggers and the circles represent the early scheduled triggers. Then you can see that sometimes the scheduler intervenes to guarantee that there's no conflict and still keep the system under control. Concluding, here represented scalable models for traffic of event-triggered control, where the number of states do not scale with state space dimension. It's also scalable because only convex optimization is needed when computing the transition system. This is the first exact traffic model for PETC. Our predecessors all were doing approximate simulations, and perhaps as a drawback, there is a trade-off between non-determinism and the system size. So our system is very small in the number of states, however, it's quite non-deterministic. This is tied to future work. Can we do tighter relaxations or even computer transition maps exactly so that we don't get spurious transitions and then reduce the non-determinism? Or even can we obtain a bisimulation in a sense that there is no spuriousness even in the long term? Well, the answer to these two questions is affirmative. This is work that we have just published in the Control Systems Letters and hopefully we will present at CDC. Finally, our work assumed a very ideal case where there were no disturbances and the controller was very simple state feedback. So introducing uncertainties, disturbances, or more general control structures is subject to future work.
With that, I would like to thank you for your attention and enjoy the conference.